Hello Level 3s. We're going to look at nuclear reactions, and that is chapter 12 in your Bendel text. And you might remember from last year that we looked at radioactive decay. So we're just going to first in this lesson review what we did last year so that all of this is a good reminder. So this is a photograph of the sun where nuclear fusion occurs. So that's the small nuclei that bond or fuse together under high temperatures. So first going to look at writing balanced nuclear reactions, and then we're going to look at the energy mass conservation law. So all particles or elements beyond uranium are only produced artificially, and that's done by bombarding nuclei with high-speed particles such as protons, neutrons, or alpha particles. And so just to remind you what these particles look like, how they're written, the hydrogen nucleus is written 11H or 11P. Helium nucleus is written 42 helium or 42 alpha. Neutron is written 1 with a 0 beneath it. N, sorry, my stuff doesn't quite line up. A beta particles 0, -1, negative should be in front of the 1, E or 0, -1, curly B, and a positron we won't really use. Just a reminder about writing beta decay equations. So if you recall beta decay, what happens there is that the nucleus, I beg your pardon, a neutron in the nucleus decays and becomes a proton plus a high energy electron or high speed electron. And so when we write out the equation, the mass number stays the same, but the atomic number, so that's the number of protons, increases by 1. And that's because of this. It's going to have 1 proton after the decay extra, right? But the number of neutrons and protons together remains the same. Then for alpha decay, the atomic number becomes 2 less and atomic mass drops by 4. So, for example, here's uranium decaying to thorium. So 238 becomes 234, 92 becomes 90 plus 2. So you can see that the atomic number on the left and on the right are conserved, and the atomic mass at the top on the left and on the right are conserved. So you need to check that. That was alpha decay. What other quantities are conserved in nuclear reactions? Momentum and mass energy are the other 2 things that are conserved. So we can, this was worked, momentum was determined to be conserved from cloud chamber photographs where the speeds of particles can be estimated from the tracks that they make, and calculations could be done to determine that momentum was conserved. So that's just to summarize: 4 quantities are conserved: mass number, atomic number, momentum, and mass energy. So just a reminder about mass energy. So where initially this came from confusion or puzzling about where the energy came from when uranium or radium underwent radioactive decay. And so that's when Einstein's theory of relativity began to give answers. And what it basically says was that mass is a form of energy. So in a nuclear reaction, the rest mass of the product can be more or less than the mass of the reactants. But the point is that the difference in the masses between left and right, between products and reactants, is due to either a loss or a gain of energy. And it can be calculated by using E is equal to delta mc squared. So for example, Rutherford observed that when he placed an alpha source inside a container of nitrogen gas, that it produced oxygen and hydrogen. And so what he did was he was able to, or what we can do rather, is that we're able to look at the energies, so the rest masses. So if you go to page 206 in your text and work through that example, we can do it in class, you will notice that the total mass before the reaction is less than the total mass after the reaction. So what that means is that there is an increase in the rest mass, and therefore this increase in the rest mass is equal to a decrease in the kinetic energy, and that can be calculated from E equals mc squared. So we'll talk about this some more in class, and we'll also do the activity questions on page 207. Make sure you've taken your notes before you shut off this video clip, or take them from the slides in your folder.